Welcome to the last video in section 2.1 on the graphs of vector curves. In this video, we're going to cover example 2.1.3 and example 2.1.4, and of course, takeaway 4 that's in between the two. So example 2.1.3, we're asked to show that the curve or the vector function r of t, which is cos of t sine of t, is a parameterization of the unit circle. And then we're asked afterwards to find a different parameterization, because we remember that parameterizations are not unique. So the first thing that we're going to do is take stock of what we have here, and in the x component we have a function, so we can say x of t is the cosine of t. In the y component we have the sine of t. And to show that this is a parameterization of the unit circle, well, we want to show that it satisfies the equation of the unit circle. The unit circle is a curve, a one-dimensional object, and so is our vector curve. And so if our curve satisfies the equation, it is a parameterization of it. And so we're going to plug in the x, the sine is the y, so we're going to plug in the x component, so we have cos squared of t, plus the y component, sine squared of t, cos squared plus sine squared. That is the most famous Pythagorean identity. That gives us 1, and so the unit circle's equation is indeed satisfied. Now we are looking for, so I guess we should write a little conclusion, therefore r of t is a parameterization. As a parameterization of the unit circle. Now we're asked to find a different parameterization, and the easiest thing to do would be just to switch our x and our y components. So if we had sine of t and cos of t, that would be a different parameterization, but there's infinitely many different ones. I could put in 2t instead. I could put a negative in front of either or both components. There's many different parameterizations, although the one that is given in the question is probably the classic or the quintessential parameterization of the unit circle. Part B says find a parameterization of the parabola y is equal to x squared. So the first thing that we might do to do this is to say, well, let's let x be a function, x of t, and give it a parameter, t. Then our y, which will be a function y of t, is supposed to be x squared, which will then just be t squared. And so our vector function r of t can be given as t and t squared, and that obviously satisfies the equation y is equal to x squared because we built it so that it would, and so r of t is a parameterization of the parabola y is equal to x squared. And that brings us to takeaway 4, and which is in R2, the vector function r of t, which is t and f of t, is always a parameterization of the graph of the function y is equal to f of x. Example 2.1.4. So now we're given here a space curve. So we're in three-dimensional space. R of t is t, t squared, and t cubed. This is an example of a curve called a twisted cubic, and we'll take a look at the graph of that in just a moment. But we're going to work purely algebraically to start with. We're asked to describe the curves that are the projections of this twisted cubic onto each of the coordinate planes in R3. So what does that mean algebraically? Well, let's again take stock of what we have. We have x is t, we have y is t squared, and z is t cubed. And so if we were going to look only at the x-y relationship, which is like projecting onto the xy plane, and I will show you a picture of that in just a few minutes, well, the relationship here is that y is equal to x squared, isn't it? And so the projection down onto that plane would be a parabola. Now, if we look at the relationship between z and x, so into the xz plane, well, z is x cubed. And so the projection of our curve down onto the xz plane would be a cubic. So there's the typical shape of a cubic function. And lastly, onto the yz plane. Well, if we look here, y is equal to z to the 2/3, isn't it? And that is a shape that you might not be familiar with, or maybe you've seen that before. It's a special kind of root function, right? The cube root, the 1/3 power, is the same thing as the cube root, and so we've got the cube root squared, and that is a cusp function, which you may have seen when you were discussing non-differentiable points in your calculus course. So let's go and take a look now at the graph of the twisted cubic, and I will show you the projections of all of these down of the curve down onto each of the coordinate planes, and we'll actually see these shapes. Here is the graph of the twisted cubic t squared, and t cubed, and you can see it's a big swooping space curve that is indeed twisted and comes up, swoops, hits the origin, and comes back down. Now we want to take a look at the projections onto the coordinate axes, coordinate planes, and so let's look straight down the z-axis. Here's our z-axis running here. So if we look straight down the z-axis, we're going to see the projection onto the xy plane. Right? And I can't quite get it straight up. Can I do that? Pretty close. So if we look straight down that z-axis, it kind of disappears, and we see the xy plane, and we see the parabola shape that we predicted algebraically. So now let's look straight down the y-axis, which means that we want to look at the xz plane. So if we look straight down the y-axis, so that it disappears almost, we've got the x and the z plane. It's rotated a little bit. Let's see if I can fix that. Maybe more trouble than it's worth, but you can see the cubic shape appearing, the projection onto the xz plane. And lastly, the yz plane. So if we take and look straight down the x-axis, again, we want this rotated a little bit to see the correct shape. Let's see if we can get that facing up the right way. If we look straight down the x-axis, so my z-axis is backwards, but it's symmetric anyway. There is the z and the y, and we have the cusp shape that we were talking about algebraically as well. So in the next video, we are going to examine the derivatives of vector functions and interpret those geometrically in the graphs of vector curves